Okay, question 6 for HL, 9 for SL. So this is a slightly tricky. It's a upper lower bounds question. So each length, we have a triangle. Each length is measured correct to the nearest meter, and the angle B is measured correct to the nearest 5 degrees. Calculate the maximum possible area of the field. Okay, the first thing to get straight is, are we trying to find the upper bound or the lower bound of both the lengths and the angle? And the answer is for the, well, it's different depending which one we're doing. For the lengths, if you think about a triangle, right? We're trying to get a maximum area of a triangle. Do we want these lengths to be, if we increase the lengths, do we increase the area? And the answer is, yeah, we do. So let me say, for example, imagine we had this triangle like this. Now, if I increase the lengths of the triangle, does the area increase? Well then, yeah, of course, the area increases. So we want the maximum length. We want these lengths to be big. Now, that's the more straightforward part of it. What about the angle? Well, okay, here, imagine these are my two sides here. Now, if I increase the angle, do I increase the area? Well, no, I actually don't, because look, as the angle, imagine that angle gets super big. The area of this triangle is now actually super small. But I don't want it to be too small, because if I decrease the angle down to, I don't know, down to here, the area also gets tiny. In fact, the angle that gives the biggest area is actually the angle 90 degrees. But because this angle is at 105 degrees, I want this to be small. So, to clarify, I need to find the upper bound of the lengths and the lower bound of the angle. That will give me the maximum possible area. So I'm actually going to write that down. Max area. I'm actually going to write this down to show the examiner I know what I'm doing, and I'll get a mark for this. Max area, I need upper bound for lengths and lower bound for angle. Now, as I say, guys, if this angle was like 70 degrees, you'd actually want the upper bound of the angle. You want the angle that gets you closest to 90 degrees, or even 90 degrees if that was an option. So, lengths, upper bound. Right, what's the upper bound of 56? Well, it's measured correct to the nearest meter, so the upper bound has to be 56.5, and the upper bound of this has to be 82.5, and then the lower bound of the angle, so the angle is correct to the nearest 5 degrees, so the lower bound has to be 102.5. Now guys, if you're unsure about what I've done here, go back and watch my lesson on upper and lower bounds. It explains it in a bit more detail. So these are the upper bounds for the lengths. This is the lower bound for the angle. And now I just use my area formula, which is a half AB sine C, if you like, which is a half. Remember, this AB sine C does not apply to this particular triangle, so it's just this side times sine of this side. So 56.5, remember we're using these, times 82.5 times sine of this 102.5 degrees. Just make sure your calculator, especially guys if you're in HL, SL, you're always in degrees, but if you're in HL, you do need to know what a radian is. So we're in degrees. So I'm going to do a half, which is 0.5, times 56.5, times 82.5, times sine, which is here, 102.5. This gives me 2275.38. 2275.38. And it's in, well, these lengths are meters, so this has to be meters squared. Does that kind of make sense? Well, yeah, not bad, because if this was a rectangle, 80 times 50 is 4,000, so something close to that. I always like to just check that the answer is not totally crazy. So yeah, that seems about right. Okay, that's it for question 6 AIHL 9 SL.